What's up, physics friends? So today I'm going to work through a mechanics example, but we're going to use something called Lagrangian mechanics instead of Newtonian mechanics. So Lagrangian mechanics is a little bit more sophisticated than Newtonian mechanics. There's a little bit more prerequisite mathematical tools that are required to solve problems using this type of mechanics, but you'll see that it tends to be a little bit easier when you get problems that become a little bit more complex for something like Newtonian mechanics to solve. Now, this example is something that's quite easy to do in Newtonian mechanics as well, but that's okay because it's just as easy in Lagrangian mechanics if you understand what you're doing. So let's work through. We've got a particle that's only moving in one dimension, which we're going to denote as the x-axis, and it's subject to a force, F equal to minus kx. And we want to find the equation of motion for this particle. So using our little diagram here, we've got our particle moving in this x direction, and it's subject to a negative force here, because we're going to denote the right to be our positive direction on this x-axis. So first things first is, for Lagrangian mechanics, we're going to set up what's called the Lagrangian. And the Lagrangian just relates the kinetic energy and the potential energy, such that the Lagrangian equation is equal to the kinetic energy minus the potential energy, T minus U. So first things first, we got to go ahead and figure out what our potential energy function is. And the way we're going to do that is we're going to use the force that they gave us. So if our force is equal to minus kx, we can find the potential energy function if we remember that a general force is equal to the negative derivative of our potential energy function. So in order to solve for the potential energy function, then we would need to integrate both sides, and then we would take the negative integral of the force, and that'll give us our potential energy function. So that looks something like this in general. And for our specific potential energy, it's a potential energy function of x, because we have a force that's a function of x. So setting up for our specific scenario, we're going to have that u of x is equal to the negative integral of f of x dx. So plugging in our f of x, it's going to be negative kx. So those negatives are going to cancel out in our integral. And we're going to be left with the integral of kx dx. So solving that integral using our power rule for integration, we're going to have that u of x is equal to 1/2 kx squared. So now we're going to go ahead and plug into our Lagrangian. So for our kinetic energy, it's just going to be like any particle moving in one dimension. It's just going to be 1/2 mx dot squared. So if you've taken intro physics, you're familiar with kinetic energy being 1/2 mv squared. So this x dot is the same thing as v. The dot notation is just a time derivative. So the first time derivative of position is velocity. So x dot here is just our velocity. And subtracting our potential energy function that we found here, we're going to have that our Lagrangian is equal to 1/2 mx dot squared minus 1/2 kx squared. So in order to find our differential equations from this Lagrangian, we need to plug it into what's called the Euler-Lagrange equation. And this is where the prerequisite math comes in, because in order to figure this out, you need to understand how to do partial derivatives, which hopefully you'll see through the rest of this example is really not that hard. You just kind of have to get a feel for it. And that's something you learn in Calc 3. So if you haven't done it yet, you will soon. So in general, this Euler-Lagrange equation is the partial Lagrangian with respect to q sub I, which is our position coordinate, is equal to the first time derivative of the partial Lagrangian with respect to q dot sub I, which is our velocity, our general velocity, And so for our specific situation, we're going to be doing the partial derivative on the left with respect to x, and on the right, we're going to be doing the partial derivative of the Lagrangian with respect to x dot. So go ahead and set that up, and it's going to look something like this. So solving the left side first, if we take the partial derivative with respect to x, the only piece of this Lagrangian that has any relation to the x variable is just this second piece here. So this is just a simple power rule derivative. We're going to take the 2 down, it'll cancel the 1/2, and our partial Lagrangian with respect to x is just minus kx. Similarly, we'll do the inside on the right side first, and that is the partial derivative with respect to x dot, and the only part of this function that has x dot is this piece here. So similar to this one here, it's just going to be mx dot. And taking the time derivative, that's just going to add another dot to our x here, and we're going to be left with minus kx is equal to mx double dot. Now that probably looks familiar from Newtonian mechanics, right? Mx double dot is just ma, and then we've got our force over here, and if you remember Newton's second law is F equals ma, so that looks very familiar. So now let's go ahead and try to solve this differential equation for our equation of motion. So what we're going to do is on our left-hand side, we'll go ahead and isolate x double dot, which is going to give us that x double dot is equal to minus k over m times x. So we're going to let this k over m constant be equal to omega squared. And you'll see why in a second that that's going to make things nice and clean for us. So rewriting with that substitution, we'll have x double dot is equal to minus omega squared x. And so in order to solve this differential equation, we know that our x function, right, the second derivative of our x function is equal to a squared constant term times our original function. So this is going to be something that's repeating. And typically functions that repeat when you do derivatives are exponential functions. So we're going to guess that our x of t is equal to e to the alpha t, where alpha is just some constant we're going to try to solve for. And that way, when we take two derivatives of that x of t, we're going to get that x double dot of t is equal to alpha squared e to the alpha t. So now if we go ahead and plug this in for our x and plug this in for x double dot, we're going to see alpha squared e to the alpha t is equal to minus omega squared e to the alpha t. And those e to the alpha t's are going to cancel, and now we have a way to solve for alpha. So we're going to find that alpha is equal to plus or minus I omega. So now that we know this piece, we can go ahead and say in general that our x of t equation is going to be c1 e to the I omega t plus c2 e to the negative I omega t. And we can rewrite this using Euler's identity relating exponential functions and trigonometric functions. We can rewrite that x of t is c1 cosine omega t plus c2 I sine omega t. And now we can just solve for our constants. So if we assume that at t equals 0, we're at x naught, which is our initial position, we'll find that c1 is equal to x naught, because when you plug zeros in, this goes away. This is just 1, so x naught equals c1. Then taking a time derivative of our equation, we're going to find that when you plug in a 0 to this piece, you're going to get this term canceling, and on the right side, you're going to get c2 I omega times 1, because cosine of 0 is 1, and we're going to let that be equal to our initial velocity, x dot 0. And so going ahead and solving here, we'll find that c2 is equal to x naught dot over I omega. And if you plug in those constants, you'll see that the I will cancel when you plug in c2, and we're left with x of t is equal to x naught cosine omega t plus x dot naught over omega times sine omega t. And that is it.